right? Does anybody remember what the content of this theorem was? What did it say?
Wait, Professor, can you repeat that? You kind of lagged on me.
Oh, sorry. So we are wondering what the theorem Schroeder-Bernstein said. What was the content of it?
We said if you have two sets, I guess, A and B, and you have an injection from A to B and also an injection from B to A, then A and B are like in bijection with one another.
That's right. So what is written here is that if I have two functions from alpha and beta, we can change alpha and beta to A and B if that's more familiar to us. And I have a function g from B to A. I also have a hypothesis that F is injective. Another hypothesis that G is injective. Now, from all of this, Langi, can you, how do you say? I hear
Oh,
your,
sorry.
I think.
I forgot to mute, sorry.
Yeah, thanks. Then we can find a function which is bijective, right? So this function h, actually, it's not either of f or g. It's just a new function that is constructed out of them, right? So this is one way to phrase the theorem if we wanted to, but we can also phrase it in terms of implications. So we could say we are given two functions f and g, right? And we could phrase it to say if f is injective and if g is injective, then the final conclusion would be that there exists such an h, a function h, which is also injective, which is bijective, sorry. Does this make sense? Okay, so I've written sorry here because we don't know the proof yet. But first, I want to prove it for a special case. Maybe from there we get some ideas, and then we can prove it in general case where types are A and B. Right? Any questions so far? Okay, let's say actually we wanted to prove this immediately. So where do I start? What do I do?
Wait, sorry, I think I'm still unclear on the difference between A and alpha and B and beta.
Very good question. So I forgot to change this as well. The way that
Okay.
was alpha and beta had no relationship with A and B, and it was just wrong because we could not prove that. But yeah, alpha and beta should be A and B. Thanks. So what are we trying to prove? What sort of connective is that? So here what we are trying to do is actually we are saying if f is injective, then something else follows, right? So I have this connective here, which is implication. So the bracketing goes like this. And now, because we are trying to prove namely this one. And therefore, since we are trying to prove an implication, what we need to do is to introduce a hypothesis, right? And the name of this, this hypothesis says that f is injective. Okay, how do I do this? What's the tactic for that?
Do you start with the constructor or?
So constructor is for introducing a conjunction, right? Or trying to prove a conjunction. But here we are trying to prove an implication. There is something else. I'm essentially saying that let f be an injective function, right? We are trying to say let f be an injection.
Would you use intro?
Exactly. So I would say intro and probably give it a name, right? Let's say intro injf. So that would be simply a proof or a witness that f is injective. So that's what it says. So this says, yeah, let f be an injective function. And we have another hypothesis, which is now we are actually, our goal is this inner implication, right? So the goal is if G is injective, then something else. So then now I'm saying that let G be an injective function. So again, I use intro. And now my goal, it's the final conclusion, which is there exists a function from A to B, which is bijective, right? So now we want to show that there is, or there exists, a function H, which is both injective and surjective. Okay. And so here's the hard part, right? So how do we prove an existential? Like, how do I prove like there exists something? So I guess the crucial part is there exists this part. I'm not sure if we spent as much time on exist. Did we do an example of exist before?
If we did, I don't remember.
Okay, so maybe it's a good idea to go over this if we didn't. So let me go to this, instead of sets, going to logic folder and open the file predicate again. And try to maybe recall this and then come back to the file we were in. So there is, from line 305, there is this section called exist. And here, essentially, we are trying to prove some existential statements, right? So here's an example. So we are here. Here, there are a bunch of examples, actually. Let's try to solve them to sort of get started with existentials. So here, what it says is like, we are trying to show that n being odd as a proposition is the same thing as there exists an integer k such that n is 2k plus 1. So this is big. I wrote riffle and riffle works simply because the predicate odd n, or the predicate odd, is defined in such a way that these two statements, like the left part and the right part, are exactly the same. So this would work by reflexivity.
Can you explain that again? Why reflexivity works?
Because odd n, which means is defined exactly as the statement like this. This is how it's defined essentially. So that's why reflexivity works. And to see how it's defined, actually, you see, like, if I mouse over this, exactly says what definition is.
Okay, so the notation is there's an odd integer n, which equals like a k value that's an integer. So there exists.
No. So odd is a function or is a predicate, right? Which takes a natural number to a proposition. So I can apply odd, for example, to number 2, right? Now this would be a proposition because Lean says so. Odd 2 is prop, right? But what is a prop? What does it say? Well, it says 2 is odd, which is clearly false, but nonetheless it's a proposition, right? Or is an odd integer, to be more elaborative here. So this guy, odd n, that's going to be a proposition. And this guy, the rest of it, it's also going to be a proposition, right? And now we are saying these two propositions are the same, or they are equal, which basically means it's an if and only if statement between them, right? So maybe I should have written if and only if between them. That would have been more clear. So if I don't put brackets, it would parse it like that. It would parse two sides as propositions. Does that make sense?
Yes.
Great. So still riffle works. How do we explain this? Because now it's not equality, but it's an if and only if. So if actually you mouse over this, it says there is such a thing as principle of propositional extensionality, for which when we have like two propositions and there's an if and only if between them, then they are made to be equal. So this principle just makes any two logically equivalent propositions to be equal. And after that, automatically riffle works, right? So there is some idea behind why riffle works here. But essentially, whenever you see if and only if, you can just treat it as equality of propositions. Any questions about this? Okay, so I guess the moral here is like, take definition of odd n to be this, and that is a check that it is indeed the case. Now we are trying to prove statement, which is if n is an integer, and if I have a proof that n is an odd number, then I want to prove that the square of that number n is also going to be odd, right? So this we can check, right? For example, if like 3 is odd, so 3 squared is also odd. So this is a proposition, and let's say if we wanted to prove this, how do I prove this?
We say that like since 3 is an odd integer. I don't know exactly how to like go about that.
So to prove anything is odd, right? We have to find a k such that that number, whatever it is, it's 2k plus 1, right? So to see that Lean understands this, one thing we can do is like, this is our goal, right? And we have no hypothesis currently, like because the left-hand side of this is empty and the right-hand side we have something. So we cannot use any of our assumptions because simply we don't have an assumption. But one thing we can do is to unfold definition of odd. So we can do unfold odd. Okay, that something happened and our goal changed. Our goal became an existential statement, right? That now the goal is to prove that there is such k, integer k, such that 3 squared is 2k plus 1. So now our goal is to find such an k. How do I do that? What is the k that satisfies that equation?
It's 1, but like, do we set 3 equal to 2k plus 1 or?
So you propose k to be 1? So in fact,
I'm thinking of 3. If it's going to be 9, then it's going to be 4.
4, right. So k4 should work. Yeah. So what do we need to prove? First, we need to provide a number. So you propose 4. So let's use it. We can do this by use 4. And now the goal reduced. So what it did, it substituted that k to be 4, right? And now we have to prove the rest of the statement that in fact 3 squared is 4. So that you can prove by reflexivity because they're just. Right. Now, if instead of 4, I propose something wrong, let's say 3, then refl wouldn't work here. So I would be stuck. So it's important which number we choose. Okay, so that is how we actually prove an existential goal, right? If our goal is, let's recall here. So after unfold, my goal is existential, which means like it starts with an existential quantifier. Whenever you have such a goal, then you have to pick a candidate which satisfies the statement. In this case, 4 did that. Okay, great. So let's do a more complicated example. So we can, you can do the similar thing, but instead of 3, you can choose 5, right? So here, 4 wouldn't work because I want to find a k such that 25 essentially is 2k plus 1. So I think if I choose 12, it should work, right? So my k is 12 in this case. Now, there's a pattern here, right? The pattern is whenever n is odd, then square of n is also odd. So we just witnessed this in 2 examples, but it's more generally true that for any odd number, this is the case. Okay, I could have done unfold. Or you could do simplify odd at star. This means, so if I look at the state of the proof, in the hypothesis, I have statement odd n, and in the goal, I also have odd, right? And I want to unfold all of them at once. Whenever you write simp odd at the start, it means simplified everywhere, in hypothesis and in the goal. I could have as well written unfold, and that should work as well, except that unfold doesn't have bracket. So that also works. So simp and unfold here are quite similar. They just expand what the definition is. But if I did simp odd, that probably doesn't work. That only simplifies the goal, right? But I want to simplify the goal and the hypothesis. So that's why I write at the start. Any question about this?
Yeah, you kind of lost me at the star.
Okay. So our goal now is to prove under the hypothesis that n is odd, that n squared is odd, right? So if like before, I do unfold odd, which basically unfolds the definition of
odd,
right? Then I get something like this. There exists k such that n squared is 2k plus 1, and that is our new goal. But actually, that's not enough, because I also want to unfold the hypothesis, right? That also has some odd, and I want to really see under the hood how it's defined. So I want to unfold this predicate everywhere, both in the hypothesis and in the goal. So if I write at start, it means unfold it everywhere. Okay, so now we need to provide a k such that n squared is 2k plus 1. Now, we don't know anything about n except this one, right? So there's no way that I can directly provide such a k. I mean, is it 10? Is it 11? I don't know, right? So we have to somehow break down this hypothesis Hn to get some useful information to prove the goal. So to break down so here we are not proving so we are proving an existential, right? But we want to do something before it, which is to use an evidence or witness of an existential quantifier. So now we want to, actually my style is to write these comments just before the line. So one should pick a uniform style. So now we want to break down the assumption Hn to gather some information about n, which is useful for the goal. Therefore, we need to eliminate the existential quantifier. Does anybody remember how we eliminated existential quantifier? Maybe we actually didn't cover it. It's possible. So to do this, we actually use this syntax called obtain. So let's think about it. What does Hn contain? Hn provides basically a number k with the property that n is equal to 2 times k plus 1. So in fact, Hn says two things, right? It provides, let me write it in a new line, provides two things. First, which I would like to call it data, which is a number k. And second, the property that n is 2k plus 1, right? So this property is about k, not about n. So it provides a data k and some property of k, basically. So if I want to obtain these two things, I use the syntax obtain. So from Hn, I obtain two things. K, which is, I just added to the context, is an integer, and Hk, which is exactly the property, right? Or if you like, you can call it value and property, if that. So now I have a value, which is an integer, and a property of that value. I want to pause here to make sure everybody understands this point. What's going on here?
I think I understand.
Okay, great. We have more examples to test our understanding, but So for now, okay, so maybe a stylistic question. Do you like this val prop or n and k and hk?
Val prop.
Is that true with everybody? So before that, it was like k
Tyler
and...
sounds good.
Okay, great. Now, how do I use this val and prop that I just generated in the previous line to prove the goal?
And I use val or
Sure.
like, oh, okay. I thought I was good. I was like, oh, okay. Okay. Val provides the value, like the data.
Mm-hmm.
What if I couldn't I use both?
Yeah, sure. You can use anything that is before this blue so-called turnstile. So anything before this, it's up for grabs. But now, yeah, we are looking for a K. For a new, maybe K. This time is not n, but n squared, right? Is 2 times K plus 1. Right, how do we find this? Maybe we do a simple calculation. And in fact, Lean supports doing calculation. So I can say that I have n squared, right? And somehow I want to find some k such that n squared is 2k plus 1. But what is n squared? That is n times n, right? So this we can just prove by REPL, I'm guessing. Ooh. It should work. So let's not worry about this for now. And n itself is equal to 2 times val plus 1, right?
Right.
Well, I'm going to multiply that by itself. And this should be true because of prop, essentially. So I'm going to write by substitute. Remember, we discussed rewrite a lecture ago, actually, on Thursday it was. So I'm going to rewrite or substitute along this equality that n is 2 val plus 1. And finally, I want to sort of like distribute this addition over this multiplication, right? So if you actually so I have to multiply this factor by this factor. So that gives me 4 times val squared. What else do I get? I get 2 times val times 1. So that's going to be 2 times val. Then I get 1 times 2. So that's going to be 2. And then I get 1 times 1. No, I think I'm making a mistake. Yeah, 1 times 2 times val. So this is 2 times val plus 1. Is this okay so far? So this is by bunch of distributivity. So I can call the name of the lemmas to do this. But there's a very powerful tactic that does all of these things without knowing the name of distributivity of multiplication or addition and those kind of things. And the tactic is called ring. So ring should take care of this. And now let me, okay. So I can certainly, so what I want is like some k. So I want to express this in terms of 2k plus 1, right? So if you look at the expression above, I have already 1. So I need to somehow factor out 2 from all of this sum. And that we can do, right? Because the first expression would be 2 times val squared. The second one, well, just val. And finally, the other one also would be val. I'm guessing ring should work as well here. Okay, so we have one error. That was a question.
Professor, just could you go over what does ring do again? Like, is it just simplifying it or?
Right. It does simplify it, but it uses the fact that, so let's see, let's try to give a sort of zero example. So I have ABC net or something, and maybe int, just to be similar. And I want to prove that A times B plus C is equal to A times B plus A times C. Well, how do I prove this? I need some lemma from the library that tells me, from Mathlib, that tells me multiplication distributes over addition. That's essentially what this is, right? So I'm going to rewrite, probably the name of this would be mul add or something. Right, so if I mass over this, it exactly says what I want, right? So this proves what we wanted, right? But here, if you look at this expression, it's a multiplication of 2 things, right? It's some A plus B, and this is some C plus D. So let's try to do this more complicated one. So I have 2 terms here, A plus B. And here I have C plus D. Now, C and D happen to be equal to A and B, but in general, they don't need to be, right? So this can, if we actually distribute all terms over this multiplication, all additions over multiplication, I should have A times C plus A times D plus B times C plus B times D. Okay, how do I prove this now? Any suggestions?
You could calc.
I can calc, but I also want, so yeah, because I want to justify these steps. So I don't want to do calc because I want to prove it without calc so that we obtain some insight essentially. Langi, you are quiet today.
Sorry, I have no clue here.
Okay, so maybe we can get some idea from the previous one. So I can look at this A plus B as a single term, right? And then it becomes something similar to this. So I can definitely use mul add, which is multiplication distributes over addition. So this would be one single term, then I multiply it over this addition, right? So if you write like, instead of AP sum S for sum, then this would be S times C plus S times D. So that step I can already do. So maybe we start by doing this rewrite mul add and make some progress at least. Okay, our goal got a little bit simpler. So remember, before that you had to prove this multiplication is equal to all this addition of 4 terms that we have here. But after this, the left-hand side got changed, right? So I have A plus B times C plus A plus B times D. The right-hand side didn't change. So we did just rewrite off the left-hand side. We sort of reduced this to what is written here, this two sum. Does everybody follow in this step what happened? Good. So now maybe I want to simplify A plus B and times C. I mean, that step can be simplified because now I'm sort of distributing not addition over not multiplication over addition, but it is multiplication over addition, but from the other way around, right? It's like first addition and then multiplication. So I'm guessing maybe here would be rewrite add mul or something would help. So if you mouse over add mul, it says exactly what we need to do. Like A plus B times C is A times C plus B times C. Because before that we had exactly A plus B times C. So if I do rewrite of this, then I got, simpler terms. And I want to do the same for A plus B times D. So I'm going to write twice, rewrite. Okay. Now let's compare the left-hand side to the right-hand side. On the left-hand side, I have A times C. On the right-hand side, I also have A times C. Right. Here I have B times C. On the right-hand side, I also have B times C, right? Left-hand side, I have A times D. Right-hand side, I have A times D. Left-hand side, I have B times D. I also have B times D on the right-hand side. So they have exactly the same terms, except the order of addition is different, right? So, so essentially here, informally, you would cancel the terms out, right? So for example, you can start canceling A times C from both sides. But so you can try to complete this. I'm not going to do that. So you need like maybe some lemma like sub self or sorry, add self. Wait, apparently there's no such lemma. Okay, I don't know what the name of the lemma is, but there's a tactic that gives you the name of lemma, and that's apply question mark. But let's try this later. So I want to put sorry for this. This would be a complicated. So for now, all we have to do is like to cancel the terms that are the same and just use commutativity of addition to prove this. The point is.
Can I ask a quick question?
Sure.
So I guess say you didn't know that add mul was a thing or it didn't exist.
Yep.
I guess my question is, it seems like you could have also used commutativity of multiplication and then used mul add again. So I was just wondering if there's a fact name for like commutativity of multiplication.
So you can check these things. So for example, let's see what does Malcolm says, right? It says exactly what you want.
And how would you have like found all of these?
Right.
Is there like a way to like know what they are called or like what they're named?
There are multiple ways, but we haven't got to that point. But I think that's a good question, so I have to answer it now. We cannot just postpone these things. So generally speaking, so if I like click on this name, you will find that this is proved in some library, which is commutative semigroups, right? So which means these lemmas are proved in more generality than just natural numbers and integers. They are proved for any commutative semigroup, whatever that is, right? So that's just a structure that has like a binary operation, which is commutative. So integers are like that, natural numbers are like that. And once you prove it at that level of generality, it works for everything. So that's how generally in MathLib things are written. Like they are written, things are written general level of like generality. So that's that. But here perhaps like then you find other lemmas, that are relevant. So for example, here another lemma which says A times B equals to A times C, and you can cancel A from both sides and get B equals C, right? Now, this is not true for any semigroup, but there are certain semigroups which are left cancellative, and for them, this is true. Now, integers turns out to be maybe just positive integers, a left cancellative semigroup, right? So you can definitely explore these libraries, but maybe that's not the most efficient way to find dilemmas. The most efficient way, I think, is like to look at, one of the most efficient ways to look at certain proofs that are in the source folder here. Like if you go to source folder and like, for example, look at logic, calc, then you will find that, I prove some identities like this with ring, but I also give like maybe before that some proofs without ring in some of the files here. So it's good to look at these things and be familiar with sort of like which lemmas are most useful. And once, when you have like, once you learn that that there is malcom, then you can guess yourself that there must be something mal-add, right? Because that's also, addcom, that addition is commutative. So you can guess certain things, right? But that gets you some, like only so far. And after that, you want Lean to suggest you these names. And that we can do, but I have to start a new file for that. So let me share different screen, because so for this tactic, apply question mark to work, we actually need a different version of MathLib, but I haven't updated to that because it would break your code. So we have to do this hopefully later with some advanced warning. So just recently, some new tactic has been added to MathLib, and that's something called apply. Yeah, so here, I think here is safe to try that. So let's say that I wanted to prove, what was like, I had 3 integers, right? And I wanted to prove A plus B times C plus D. And I have to put brackets here, otherwise the parsing would not be as I intended. That this is true, that this is A times B plus A times C. Okay. So, I mean, we can try the same, right? We can try rewrite. Actually, let's not try anything. Let's just apply question mark. So now you're asking Lean to suggest you something, right? And now you can see that these orange bars are persisting. but it will finish and tells you something, hopefully. So let's wait a little bit. Okay. Right. So here's a bunch of suggestions, right? And how do we know, like, so there's a lot, as you can see. I can just scroll. Because as you can imagine, like, there can be a lot of facts that can be helpful to prove this, right? Some of them are more helpful, some of them are less. What you can see is, like, if you did try this suggestion, for example, then Lean tells you, after trying this, your goal would be changed to this one. Now, this is not particularly helpful to have this goal after that, right? Because it basically doesn't do much. But we can scroll down to see which one can be more useful. So I'm now looking for mall add or add mall or something like this in this list of suggestions, if there's such a thing. Okay. I think we are getting closer maybe to some of the goals. Maybe not. It usually appears to be on the top if it's helpful. Okay, I don't think I'm getting anything useful from this right now, unless you see something that is useful. Maybe this one, perhaps? Not really. So maybe I know that mall add works here. So now my goal got a little bit simpler, and maybe now I ask apply. So because we are working in very basic stuff, actually, there is more and more lemmas in the library that can be used, right? Because integers are such basic things that can be instance of many structures. They can be instance of, like, you know, semi-groups or groups or whatever. So many lemmas can apply to them. Right, let's see. I don't think any of these things are useful at this stage. Yeah, I mean, we can try some of them. So for example, let's say, I'm going to do mall add again. And once, oh, I cannot do that, but I can do rewrite add mall and do it again. Okay. Now maybe at this stage, apply helps. I'm not sure. I mean, this is quite new tactic, and it's not as good as others, but sometimes it's useful when you do Lean. But we can wait to see what it suggests. Hey, it's taking its time. Okay, let's go to the top of the list and see. So it's suggesting that I can use symmetry of equality. That's not particularly helpful, I think. This really negates both sides to me, it seems. Well, that's not going to help. That's actually make things more complicated. Right, maybe this one. Well, this, what it does, it brings everything to one side. It can be helpful in some cases, not in this case, I think. What about this one? Add EQ of EQ sub. I think what it does, it brings certain terms to the right-hand side. So that's A times D. But really what we are looking is just maybe some commutativity of addition, right? So Okay, maybe this was not so helpful, but really what I want is like, I want to maybe bring A times C to left-hand side. So you can write, rewrite, add, com, and see if that helps. So if you compare with this, then you see that these two, like, right. So I have A times D plus B times D, and then some other term here. And we rewrite commutativity of the addition here. So the second addition. Well, that is maybe not exactly what we want to do, but you can provide which additions you want to like rewrite. So you can say, I want to rewrite A times D and maybe B times C or something like this. So, but it will be something complicated because we have to, go through all these expressions and see where we want to use commutativity. So that's why I try to avoid these things and just write by ring. It should work. Wait, it should work. Let me go back to our file. I mean, this ring should definitely work. I think this project somehow I'm not. Right, so we were here, right? So let's see if ring works. Yep. So in our project, ring should work. Does it work without these two? Yes. So to not go through the pain of all, this using lemmas for commutativity and distributivity, and do rewrite in the right place and things like that, we just use this tactic ring. Any questions about this? Good. I think we were stuck here and I wanted to do this calculation, right? And I think Sherry asked me, what is ring? What does it do? So I hope by now we have some idea of what ring does. But now I still have some, well, this is rewrite. Maybe let's see. Okay, I still get an error. Let's read about that error is. Expected term. Maybe I need to put some bracketing. Okay. Here I need to write multiplication, of course. Maybe I do some stupid mistake somewhere else as well that I need to put some multiplication. Let's see. Something like that. Okay, so I'll fix this later, but for now, let me just. So the candidate we wanted to find is essentially, it's this part, right? So we expressed n squared as 2 times something plus 1. And that's the whole point. So we can use that expression. So we can use this. And now you can see that our goal is to prove that, in fact, n squared is that, right? So I want to now, to actually prove this goal, we have to substitute n by 2 times val plus 1 so that we get somewhere. So let me substitute n by 2 times val plus 1. So that's going to be rewrite prop. So that's what it did. So our goal is now, they are all like similar things, similar looking things, because they have this parameter val in them. And the idea is like, if you like raise this to the power of 2, that's what you would get, right? And hopefully here ring would help us, right? So it did. Okay, so that was the proof. Sorry that it took so long, but anything in this proof that we want to elaborate on, or? Okay. I mean, here it's val plus val. You can also write it as 2 times val. It's your choice. And then use the same ring. It should work. Okay, so let's prove one more existential quantifier. So to make sure that we actually understand this. So where do I start this proof? So I know I have a number x, which is odd. I have a number y, which is odd. And I want to prove that their sum plus 1 is odd.
And we do like the what's it called? Like the obtain at start?
Unfold.
Oh, yes, unfold at start.
Right. So I'm essentially unfolding definitions of odd everywhere. So everything just got longer, you know? There's some k now everywhere. Okay, next step.
I want to say, Professor, can you scroll up again? Yeah, are we allowed to do the obtain val prop as well?
I think so, because I mean, in fact, I think this is the only thing we can do, because we know something about x, a number x, right? And we want to break it down into 2 parts to get a data and property. Same with y, and then we can combine all those things to reach the goal. So this is exactly correct. So I would say obtain a pair, because there are 2 things. And this should be hx, right? And now we can give a value and property. So y will have a value and property, and to distinguish between them, I'm going to subscript this as x and for x, right? And copy the same for y. Okay, so you've got lots of things now. You've got x, x, y, value y, prop x, and prop y. And we want to find a k now. So the goal is existential, such that this is true.
Okay, can we calc and then rewrite?
Sure. So so let's follow this pattern here. So I want to start by writing x plus y plus 1, right? So that is going to be equal to, well, I guess I'm going to rewrite x as 2 times val of x plus 1. And similarly for y, I'm going to write val y plus 1. And then there is an extra 1 that we already had here, right? So for now, I just want to write sorry, but I will finish it later. Then there's this underscore to say that, you know, there's a chain of equalities, like that guy. So underscore stands for whatever it's here. So this, whatever it's here, is equal to, and I want to like put my equality here just for stylistic reasons. Okay, so now I want to write the whole thing as 2 times some k plus 1. So I'm going to factor all of the 2's out. So this would be 2 times, wherever I can write 2 times anything. So this would be val of x plus val of y. And I, by mistake, wrote equality here. And what else do I get? Well, I get also 1 here and 1 here. So they add up to 2, and then I can factor them out, right? So it would be something like this. Okay, so let's write by sorry. And now let's try to fill the sorries. So the first sorry should be by rewrite of prop x and prop y. Because those are the reasons that this substitution should work. Now, unfortunately, this doesn't work. Because why is not this? What am I doing wrong here? I should put it like this, I think. Yeah, so that's about the syntax of calc. And then now I have to fill this, sorry, I guess. Okay, so how do we prove the last step?
By ring.
Yep. Okay, it gives us some error, which I don't quite understand what it says. Trans EQ exists. Because you see, the goal right now is to prove there exists a K, but now, so we have to write use, right? But we are saying calc. So Lean complains, it's stupid. So it complains that you're not giving me any K right now. But I think we can do have a statement now. So we can say have x plus y plus 1 is equal to, the last thing by the following calculation. Okay, now it gives a more interesting error, which is that this rewrite wouldn't do it because I have unsolved goals.
So have is essentially setting up like, okay, this is the statement that we're trying to prove.
Yeah.
Okay.
Right. So just, so this will be sort of like intermediary goal, accept it for now, and then we solve the bigger goal later. But before that, it would complain, you have to use or something. But now we are saying, okay, wait, have this for now, and then we will prove what you want later. But I'm wondering why doesn't rewrite work here? Maybe, no. Okay. Can it be? Okay, I don't know why. So I will fix this. I'm not really good with this calc tactic, but I will fix it and put it on the GitHub. But now we know what this actually, I'm not just really good with calc, but let me have a statement. So this should be true by rewrite a few things, right? It should be rewrite of prop x, prop y, and maybe after that I do ring. Yep. So calc breaks down the thing, but I'm terrible with the syntax of calc. That's why I usually screw things up. But this works, right? And you might wonder what this symbol was. Well, that's like just, writing 2 tactics one after the other.
So why are we still getting an error with the by?
That's because it's not complete. Like we haven't finished the proof yet. So if you put to test that, you put sorry, and then everything goes away, right?
I see.
But now, what is the K that you want to provide in here?
Val x plus val y plus 1.
Exactly. So I'm just going to copy this. Okay. Now I have to prove that x plus y plus 1 is equal to 2 times val x plus val y plus 1 plus 1. And this is exactly what you proved in this, right? You can also give it a name, big H or H, instead of this. And just say, you know, this is exact H. Okay, we are done. So here's the challenge, maybe. It's more complicated. So similar to predicate odd, we also have this predicate even, which says, you know, something is even, a number n is even if you can find a case such that n is 2 times k. And then this is a more complicated version, but I'm sure you can do it now. Okay, let me look at the time. Not much time is left, but maybe 1 or 2 minutes. But let me go back to the file. So I think we were at Schroeder-Bernstein file, and here the goal was an existential statement, right? And we thought, okay, we never proved actually any existential statement before this, so let's go back and see how it works. But now you have to prove there exists a function h that goes from a to b, and it's bijective. And because your goal is existential, now is the place to provide such an h. So we have to like use what? Well, we don't know how h is constructed now, right? So I'm going to use sorry and then close off the whole thing with sorry. But the idea is like, you know, fill the sky. And right now, Lean says the function sorry ax is bijective because it doesn't know what the function is. So we have to provide the data, which is use, and then prove that the data satisfy the property we wanted, which is property of bijectivity. Okay. Maybe it's a good idea to close this now, and we need one more lecture for, unfortunately, for Schroeder-Bernstein, but I mean, it's fine. We needed to understand existential quantifier. So yeah, I want to stop here, and if there's questions, I want to take questions essentially at this point.